Hey everybody, it is Stat201 on YouTube. Good to see people in the chat. It's a party, I like that right there. Good to see you there. And so we are live on YouTube. Stats never stops, you got that. We are going to do some testing today right here. This is your vacation? Good to have you then. I'm so glad to see, I think we have like 3 or 4 people watching, but that's perfectly fine. This video is going to be out in the future, so I want you guys to have something to look at. We're gonna talk over today about testing. So I'm gonna hop over to a different screen. So we're going to do all the different tests that will be on the final. That's what I want to put out here in video format. I might also chop up this video just to go through all the different types of tests. But the first thing we want to do is our 4 steps for testing. So let's write down our 4 steps. I think I'm going to write it here in big words. So let's look at our 4 steps for testing. Our 4 steps will always be the following. So please, if you're in the chat, ask questions. I already see there's one person in the chat. So anyone who wants to ask questions, ask those questions. The first thing we're going to cover today is the 4 steps to a test. So we have 4 different steps we need to make sure we do for each one of these tests. So as we do these tests today, we're going to look at the 4 different steps. Step 1, we're going to write out the null and alternative hypothesis. So we need to make sure we can do this for each one of these tests. Write the null and write the alternative. So I'm going to keep these nice and neat. We'll try to put them all to one line here. Write out that null and alternative hypothesis. Step 2, perform the calculation for the t, z, or chi-square. This is where we check the conditions because certain tests have conditions. So we'll perform the calculation for the t, for the z, or for the chi-squared. We're going to find the test statistic. So that's what step 2 is find the test statistic. So once you find that, I wish we had everyone in chat today because I'd ask my big questions. Once we have the test statistic, what will we do? Because every time we get a test statistic, let's see, I can probably draw today. I can draw. Once we get this test statistic, we are going to then find, like the red line is the test statistic. So we find, let's say it's a t-score and we're doing a greater than test. From that, we then find the what. Maybe we'll see some people in chat answering questions. But from the test statistic, we will then find, and it's that area under the curve. Oh, Morgan, great answer. Morgan, you are right. It is, it is the p-value right there. We will find the p-value for the test. Make sure to shade according to the alternative hypothesis. So key stuff right there. We will shade, nice job Julio, great job. We find the p-value, that's what we do for our 3rd step right there. Once we get past step 3, and this is for all of our steps, all of our tests, what will we do next? Step number 4, once we have this p-value, we will then do what? Because we're going to do all 4 tests for the test today. Once we have that p-value, we will do what? And let's look at the 2 scenarios we can get with a p-value. Our 2 scenarios will be a low p-value or a high p-value. So we can have a low p-value. You don't want to go that way. We can have a low p-value or a high p-value. How does that work out? Well, the way it would look visually is, generally speaking, these are the extremes. We can often have a p-value, and let's just do a right-tailed test that maybe looks like that, or a p-value that looks like this. So I'm going to shade the area under the curve right there, and I'm going to shade the area under the curve right here. So once we find the t or the z, which is where the line is at, and apparently we're doing a right-tailed test for just this theoretical problem we're doing right here, we will then shade the area under the curve to the right, to the left, or both sides. More on that as we go through testing. But what we have right here is the p-value. From here, we will do one of 2 things. We will either reject or fail to reject the null. So state your conclusion. Reject / fail to reject. These are the only 2 options. Do this in context of the problem. I'm going to put an exclamation point right there just to make it clear. Especially for your project you're working on. If you're working on the project, you'll notice you need to talk about the mean engine life. And so we'd say we have evidence that the mean engine life is greater than 3,500, or we did not find evidence that the mean engine life is greater than 3,500. We still conclude that it is equal to 3,500. So that is what we have going on right here, is we are trying to talk about it in context. You can do many different types of tests, and we'll be talking about that today. But these are the 4 steps, and as we work any one of these problems, I'm simply going to come back to these 4 steps here, and we're going to look at each one of these. Hey, Calzone Tyrone, good to have you here. This is a fan favorite in the chat, so awesome, good to have you here. So let's look at the first test we did, which is the 1 proportion z-test. So the 1 proportion z-test, remember we're going to come back to this, these are your 4 steps that we will do for each one of these tests. The first test we did was a 1 proportion z-test, a 1 proportion z-test. So I need to go back here to home, let's write this in nice and neat here. 1 proportion z-test. Let's figure out when we use this. This is key. Why do we use a 1 proportion z-test? Like, what kind of questions could we write on your test when we do a 1 proportion z-test? What kind of data leads to proportions? These are all questions you should be thinking right here. We need to do something with proportions. And you might be thinking proportions is categorical data. So if we have categorical data, that would lead to a 1 proportion z-test where we can test the proportion. So let's put in bold here, when to use. We have 1 categorical variable, and we are testing the level or the proportion of a certain level. What does this mean? We have 1 categorical variable. Oh, like if somebody owns a dog, that's yes or no. And we want to see maybe the proportion of people who own a dog is equal to a certain amount. That's what we're doing here with the 1 proportion z-test. Quick question in the chat, what's the difference between t and z, or are they completely different? I am confusing them. So here's a good thing to remember with the t and the z, and we'll go back to the 1 proportion z-test here in a moment. The t and the z and the key differences. I always say mu t, and we're going to go back to not using the highlighter. I like to say mu t p z. Now that's one way to remember it. Mu will always go with t. If you're doing mu, you're using t. And the reason is, especially in statistics, a lot of times we do not know the true standard deviation. Now there's a lot more to this with William Gossett, and if you know sigma, you'll be using z, and if you know s, you'll be using t. S and t, sigma z. It's a little more complicated than I'm making it, but at least for our test, if you're using mu, a lot of times we use t because we will assume we do not know the true standard deviation. If you remember, when we were doing sampling distributions, we actually used z. So the quick shorthand right now is if we're doing tests on the mean, we will do the t-test, which a t-test is on the mean, mu t. If we are doing z, at least for this test, not for previous ones, we will be using z on the proportion. I think I said that correctly. If we're doing tests on the proportion, we will be using z. This is because of knowing the true standard deviation or not knowing the true standard deviation. And William Gossett did some fundamental work on making the t-distribution. The t-distribution is basically the z-distribution. It just carries with it degrees of freedom. And we'll review that even more here, Morgan, in just a little bit. Great question. They're very similar distributions, but the t is basically a more exact distribution, which takes into account the degrees of freedom, which are based on sample size, and makes adjustments to the normal distribution to better calculate confidence intervals and tests. The t will become the z with infinite degrees of freedom, and oftentimes at larger sample sizes is very, very similar. Great question. We'll be talking about that a lot more, so thank you very much. 1 proportion z-test right here. The 1 proportion z-test, you're welcome. I'm so glad to hear them, Chad. I love the questions. That's why I want to answer all of them, because you're here, you get your questions answered. So with the 1 proportion z-test, what do we have? The 1 proportion z-test is for categorical variables. Think about it right now. What could we test? I say things like, let's test the proportion of students who like Taco Bell. You'd have to walk up to someone and say, do you like Taco Bell? And that answer should definitely be yes. Do you drink Red Bull? That's a categorical question right there. Categorical questions are things that are answered like yes, no, or true, false. Those put things into categories, and we just want to figure out the proportion of a certain level. So now that we know when to use the 1 proportion z-test, it's when we ask one question, and we want to figure out the true proportion of that level. We're going to test the true proportion. We need to maybe look at the notation for this. Let's look at the notation for this question. So let's hop right over here. It's got the drawing up. Is that not the drawing? What is going on? Let's click the chat thing. There we go. I don't know what was going on with that. Okay. Notation for this problem. We're going to try to put all the notes here for all of these. I'm probably going to have to draw out the notation. It's going to be easier to do. So what do we have here? That's going to be easy enough. For the notation for this test, we will have n. What is n equal to? What is n equal to for notation for this? N will be equal to the what? This will be an easy one. We'll always do this one. N will be what? Let's see in the chat. N will be sample size. N is always sample size. And then we also have for this one P naught. P naught. P naught is equal to the hypothesized true proportion. You'll notice a theme if you're watching other videos in this. P naught is the hypothesized true proportion, so mu naught would be the hypothesized true mean when we get to another test a little later on. So P naught is the hypothesized true proportion. We also have Q naught. I guess we should mention that if people sometimes wonder what Q naught is. Q naught is the complement, and I'm just trying to remember, complement with an E, I believe, complement of true proportion. And if P naught, so it's just 1 minus P naught. That's what we mean by complement. It just adds to 1, so there is P naught and there is Q naught. That's how they are found. Last but not least, I'm just thinking through the equation in my head, we have P hat. So we got to go up here to the equation builder to throw a P hat in there. I guess we could draw it, but what fun is that when we can go to equation builder? Under equation builder, we can insert a accent. You got to bend down and see where it's at. There's the hat. We found it. So we got here P hat. We'll not need Q hat, we'll just use P hat because this one will just deal with the sample proportion. P hat is the sample proportion. Basically, I want you to know how to use every one of these tests, and that's why I'm coming in here to review this today. Here is all your notation for this one. You should know all of these and know how to identify them in problems. Now that we have this written out right here, we need an example problem. Let's do an example problem. Example problem. This is going to be a very, very quick problem, so we're just kind of giving a very, very short example problem for you to kind of figure out how to do it. And I want to ask you this. If you can write fake problems like I'm writing right now, not really fake, but just any problem, if you can do that, you understand how this works. And when you get to the test, that's all we do. I just sit around writing problems. That's all I do with my whole life. No, not really. But if you can write problems out, then you're doing what we're doing for the test. The better you can come up with problems, the better you understand what we're asking you to do on the test. So let's try writing our own problem right now. Well, all we need to do is come up with a problem. UT wants to understand the true, or UT, let's do this. UT thinks the true proportion of students who think, UT thinks, all right. Let's start the question again. UT takes a sample, there we go, of 200 students. From this sample, 130 of them, 120 of them, 120 of the students believe we will go to a bowl game. Is there evidence to suggest that the true proportion of students who think we will go to a bowl game is greater than 50%? There you go, or 0.50, it's 50% too. Boom, we got our example problem. So now we have everything we need. I will add one more thing into the notation. I'm often asked this. We have right here, p hat is the formula of x over n. So let's go here and insert this. People often forget this, and this is a video I want everyone to see. So I want to put in every bit of notation I can do. P hat is equal to x, oh not s, x over n. And so that is what we have going on right here. P hat is equal to x over n. And what is x? Someone might be saying, what is x? It's lowercase x. Number of successes in the sample. So immediately you should start identifying things in this problem. Can anyone tell me, if you're in the chat right now, I know there's not a ton, but we should have n, we should have p naught, we should have q naught, we should have p hat, we should have x, we should have n, and again, all these great things right here are in this problem right here, right now. Let's see, and then this is what I would do on the test. I would take out my pen, choose a nice blue pen right here, and I would say, okay, the sample size is 200. That is n. I've identified n. This is how many successes there were, how many people reported the thing we want. There was 120 students who said, yes, we will go to a bowl game. This right here is P naught, and that makes Q naught equal to 0.50. P naught and Q naughts are just complements of each other, so when we know P naught, we know Q naught by just subtracting P naught from 1, because it has to be if it's 0.5, Q naught is 0.5. And I think that does everything except for P hat. P hat would be 120 over 200, so P hat is 0.60. Is that blocking me? Oh, it's right in the way of my head. So that is where we are at. So all I did was take x over n. X was 120. Nice job, Morgan, in the chat. Great job. So yes, that is what we have going on right here. We've identified everything for this problem. From here, let's go grab our sheet. So we've got our 4 steps to doing a test. Let's try it out. Remember, we talked about this at the start of the lecture, or the start of the little test thing today that we're doing. We're going to go down here to the end of it. We're going to put it right here. Write out the null and alternative hypothesis. So we need to write out our null and alternative hypothesis. You'll notice in this problem, I'm asking you, is there evidence? Is there evidence, okay, that sounds like I'm talking about an alternative, that the true proportion of students who think we'll go to a bowl game is greater than this amount? So I guess one more bit of notation, I hope it moves it down. This won't, I don't want to confuse you. P is the true proportion. We won't use P in the calculations because we don't know what P is. But the true proportion is P. We don't know what P is. That's what we're going to test. We're seeing if there's evidence that the true proportion is likely greater than this. We're going to see if there's evidence for that claim. So we're going to set up our test to see if is there evidence that the true proportion of students who think we'll go to a bowl game is greater than 50%. So what we have here is all of these values, identifying them, knowing in notation. I know there's P hat, I know there's P naught, I know there's P and P value. It can get very confusing. Take your notes and make sure you know which one each of these are. So definitely notation is the key to passing the test. So now that we're here to step 1, write out the null and alternative hypothesis. We just read it off. The null would be the equal sign. HO, the null states that the true proportion is equal to 50%. If you notice the question said, is there evidence that the true proportion is greater than 50%? I always ask my students to read this because here's the mistake I see on the test. I usually see this mistake. Read it now. It says the null states equals 50%. What equals 50%? What equals 50%? I see that mistake all the time on the test. And I say, read it. And it's like, okay, the null says it's equal to 50. What is equal to 50? The true proportion is equal to 50. Make sure you use the right thing right there. I'll often see things like people will put right there mu, but think we're asking students, oftentimes if you see a decimal, it's probably P, but probably, I can't say for sure it is, but we're asking students, do you think we'll go to a bowl game? So that would be not mu, it would be P, because this is the true proportion of students who think we will go to a bowl game. The null says it's equal to 50. We are looking for evidence for the alternative that it is greater than 50. So that is step 1. Write your null, write your alternative. Perform the calculation for the T or the Z. So when we perform this calculation for the T or for the Z, we need to choose the right equation. And so let's write out that equation right here, really nice and really big. And so I'm going to put it in the equation builder because that's going to be the easiest and best way for us to see it. So let's go to Insert, Equation. It's going to be Z equals, and you do get a formula sheet for our tests. So do not fear, you will have a formula sheet. And we will have the equation written here in just 1 second. This one also needs that. And this will be, we need a P hat to start it. So it's observation minus mean over standard deviation, but it's a little more interesting than that. We observe a sample proportion, and then the mean of the null distribution would be P naught. So we need a little accent, or we need a little subscript on that. We need a P naught right there. Now we're going to take and we're going to copy paste our P naught because we're going to use that down in the bottom one right here. Because right now P naught is assumed to be, you're welcome Morgan, thank you guys, I'm glad you guys are enjoying this review. P naught times Q naught, so I typed a Q right there. P naught times Q naught over N square root. So yeah, definitely come back and watch it. I want this to be here to help. That's why I'm doing it before the break, just so you can see all the different tests and how to do them. So we'll probably be going for like an hour more, but I want you to see how to do each test and when you use each test. So this is the equation, and we have all these numbers. So if you notice, we can just take our numbers from previous, and let's just drop them in right here. If you remember previously, you might have to scroll back up, but we said the sample proportion was equal to 60%. Turn the ringer off for the moment. The sample proportion was equal to 60%. Now let's copy the equation and do it. Watch this. Let's go here. Let's copy the equation. And so let's hit tab, makes it smaller. And tab again. Let's bring it back to this line right here. There we go. Tab it over. Try to make this look all nice and pretty. And we make it nice and big. So I'm going to write one of these right here with the numbers and one of them without. And there we go. So if you notice, this one right here is the standard equation. Then this one over here we're going to solve for z. So p hat was the sample proportion, which was 60%. Oy vey. That is too big. Let's go a tiny bit smaller. There we go. Okay, that'll work for now. This is the hypothesized proportion because it's p naught. You can look over there at the left on which one I'm doing. And then we need on the bottom p naught times q naught. Be careful. This is where people often make a mistake because they often use p hat down here. That is p naught because according to the null, p naught is equal to p. This is p naught. P naught is 0.5. We're saying that is equal to p according to the null. So down here on the bottom, we're basically putting p because right now we think p naught is p. So if you remember p times q over n square root, we're just doing that. Sample size 200. That's got it. Solve the equation and you've got the z. We'll talk about conditions here in a moment, but the z-score is simply going to be solving the equation. So as long as I don't make a math error, we'll be good today. P times q, or p naught times q naught, over n square root. We're going to hit that square root button. That is now the standard deviation. So I just solved the bottom of the equation. Everything you're seeing right over there, where my finger's pointing, this finger, oh, there we go. That bottom of the equation right over there is the answer, 0.035. That is the bottom of the equation. If you notice, the top of the equation is going to give us a positive z-score because it's 60 minus 50. So all we're going to do is do 0.60 minus 0.50. That's the top of the equation. We're going to divide this and get a z-score of about 2.7 or 2.8, 2.8 something. There we go. That is our z-score. Z-score found. Let's go ahead and round it to 3 decimal places. Usually we like 2 decimal place accuracy on the test. And let's double check to make sure we didn't make an error on our just transcribing of it. We're good. So you can double check your math. That's where a lot of mistakes can happen. We try to do contingent grading on the test, but we've now found the z-score. This is a z-score, and it's a test statistic, which tells us how many standard deviations away the observation was from the mean. I want you to look at this equation. All it is, when you're doing this, let's hop outside the equation builder. All it is the top part is a difference. That's just how far are those numbers away. And the bottom part of it is a standard deviation. So it's a difference standardized. A difference standardized is a z-score. Just like observation minus mean over standard deviation is how many standard deviations is the observation away from the mean. Now we're just figuring out how far away is the sample portion from the null proportion. That is the top of the equation. How far is the sample proportion from our null proportion? And then what happens when we standardize that difference to turn it into something we can use as a z-score? So that's all we're doing here, and the answer is 2.82. And you should think to yourself, that's kind of large. That's kind of maybe a smaller p-value, because the larger the z or the t or the chi-squared, the smaller the p-value. And when we say larger, at least for z and t, we're talking absolute value, because it'd be further away. Like if I'm the center of the curve right now, if I'm a normal curve, the further away you go out, the smaller the p-value would be. But anyone sounds good? Yes! Yes, Nicole, so glad to hear that. Yes, this is used throughout all disciplines. Confidence intervals, all this stuff, it's so commonly used. So glad to hear that. Thank you, Nicole. Statistics is throughout all disciplines. And you're probably like, I know how to interpret that. I'm 95% confident the true proportion of animals that will be affected by a certain illness is contained in the confidence interval blank to blank. It's the true proportion of animals that will be affected by an illness. Yeah. Or you could say on average this many animals are affected. So you could figure out how many animals are affected on average in a certain month. all that great stuff right there if you're calculating the average amount of animals affected or the proportion of animals that'll be affected. Because is an animal affected is a categorical variable, which we're doing here. And then if you collect data on maybe how many animals will be affected per 1,000, then you could collect data on that. Oh, that's so, man, I love hearing that. I love hearing that you guys are using this in other classes. Statistics is the backbone of a lot of disciplines. Anything related to science is using statistics, so we're all about that. Last drop of Red Bull. Okay, thank you, Nicole. So glad to hear that. I love it when you guys are using this in your discipline. That's what really makes me happy. All we gotta do is find that p-value now. So to find that p-value, we need to shade according to our alternative. Well, okay, so I gotta shade according to my alternative. So on the test, here's what we'd probably have you do. What you would need to do is draw out your distribution, and then you need to go here. I'm gonna put 0, 1, 2, 3, 1, 2, 3. 1, 2, 3, -1, -2, -3. Then where did I land with my z-score? My z-score, and you'll see this in our jump output, we will see 2.828. There it is right there. That's where I landed. And now, which way am I going to shade? Which way am I going to shade? If you don't remember and you're like, well, how do I know which way to shade? Go right here and look at your alternative. That is a greater than alternative. What way does that point? It points this way. I'm mirrored right now. It points that way. So since it points that way, that's the way I'm going to shade. And that is my p-value. Now I want you to think, if we had landed closer to the null, if we had landed all the way over here, the p-value would be water. Usually in class we'll have a lot of people answering, but I'll tell you the answer. The p-value would be bigger. It's like you would just take that line, here's the line, you're going to move that line further over here and there'll be more shading under the curve, telling you that what you observed was more probable given the null is true. But what we observed, at least by what we're seeing right here, looks to be what? Probable or not so probable given the null is true. Does it look to be probable or not so probable? And the answer is ours does not look to be that probable given the null is true. And I think this p-value is going to be very small. We'll show it here in a half second. Let me go up to here and let me pull down the David M. Lane normal curve. You know what? I'm going to go stat distributions again. Stat distributions, want to give them a big shout out, not that my shout outs matter, but stat distributions has a great site. And so let's take a look at the stat distribution site because they really do a good job on it. Okay. So if you remember my z-score, I'm going to go here and I'm going to put in my z-value of 2.828. And then I'm going to move out of the way just slightly here. We're going to go to right-tailed test. If you look my p-value, I'm going to stand over here. There we go, works perfectly now. My p-value is 0.002. So that is a very low p-value. So with this low p-value right here, and if you look, does this look a lot like the curve I was drawing in Word? It should. That's my goal. What I was trying to do is draw out the curve right here and then do the same thing, because we often have people say, wait a minute, how can I do that on the test? Well, you can draw it out. And we try to make it more obvious on the test. We try to make things like this where the p-value is going to be very small, because we do know that if we're doing a right-tailed test, hypothetically speaking, if we were to land right here, hypothetically, if you were to land right at 2 and you were to shade above 2, what would be the p-value then? If you landed at 2, the p-value for that area would be about 0.025. The p-value would be about 0.025, and why? Because the 95% confidence interval. 95 is between -2 and +2, and I'll reverse time here in a second on this. But with 95% between here, that would leave 2.5% outside of either side on the empirical rule. So that p-value would be 0.025. So we can give you test questions like this where we might say, do you reject the null at the 0.05 alpha? Although you can't, for 100% know the p-value, at least theoretically speaking, the p-value has to definitely be below 0.05 because we are further over. If you look where we're further over than here, and from where I just drew, from there over would be a p-value of about 0.025. So we're definitely able to reject the null here, and that's where I was going with this. That's kind of cool. We got to reject the null, but now we have the p-value. We know the p-value, and we can see it on the previous applet. That p-value, I believe, was 0.002. That's telling us that our result of 60% or more extreme would occur 0.002 or 0.2% of the time, if we turn it to a percentage, 0.2% of the time given that the true proportion is 50%. So given that the true proportion is 50%, our result of 60%, which has a z-score of this, would occur only about 0.2% of the time due to random chance variation. And think about that. That means the result is likely or unlikely given the null is true. Our result, look at the p-value, likely or unlikely. It's like, this is the probability you'll win the lottery. I mean, that'd be awesome if it was lottery. But you would say it seems likely or unlikely. This right here would be likely or unlikely given the null is true. And the answer is, it's not likely given the null is true. So when the p-value is low, reject the null. Last but not least, let's do it. Here's what we got to write out. We need to write things like, in this one especially, I reject the null hypothesis that the true proportion of students who think we will win a bowl game is 0.50. I have evidence that the true proportion of students who think we will win a bowl game is greater than 0.50. If you want to be specific, you could say my p-value is this. My p-value was 0.002, which is less than alpha, can't spell today, of 0.05. So this seems like I wrote a lot, but I want to tell you how easy it is to remember this. Let's go back to our null and alternative. Here's how you do it. When you look at your conclusion, I just want you to talk like this. I want you to go before the null and just say, I reject. I have evidence. So let's take a look at this. I reject the null hypothesis that the true proportion of students who think we will win a bowl game is equal to 50%. I have evidence for the alternative hypothesis that the true proportion of students who think we will win a bowl game is greater than 50%. Do you see how I'm just rereading the null and alternative, but as a sentence? I could summarize this to say, well, it looks like there's good reason to believe that more than 50% of students believe we will win a bowl game. I could summarize it like that because the null was unlikely. I rejected that null. Now, there is another option where we could say I do not reject the null, or i.e. fail to reject the null. Maybe we'll do that for the next one. I'll set up a fail to reject the null for the next one. But in this one, our p-value is low, and when the p-value is low, you reject the null. When the p-value is high, just let it fly. And what do I mean by when the p-value is low, reject the null? When the p-value is lower than your value of alpha, which is what we saw down here. My p-value was lower than alpha, which is 0.05. So if this p-value right here is lower than assumed alpha of 0.05 with a p-value of 0.002, which is lower than alpha, I reject the null. If my p-value had been high, what do I mean by let it fly? Let's say I landed right here. Does anyone have any idea what the p-value would be for this test? Well, look. You can probably see it now. Now the p-value for this test would be what? If you look at that test, if that had happened, I would have saw in my sample 50% because my z-score would be 0. So what would we say here? My p-value, well, that's half the curve, is equal to this. My z-score would equal to 0 because it would be 50% minus 50% or 0.50 minus 0.50, and that's a difference of 0. And thus, we landed right on the null, so there's no difference. And so does that seem likely given the null is true? If 50% of students think we'll win a bowl game, the most likely thing to see in a sample would be 50%. We're shading to the right because this is greater than test, and so what would we say here? We would change and we would say, I fail to reject the null. We don't have reason to believe that more than 50% of students think we'll win a bowl game. All I'm doing is reading that null and alternative again. I don't have evidence that greater than 50% of students think we will win a bowl game because I do not reject the null. I fail to reject the null. I hope. Is anyone in the chat? How we do in chat? Did that help maybe better explain where all these p-values and everything is coming from? I'm going to set it back up nice and neat right here so we can see what's going on. But that is your one proportion z-test, and we are 1/4 done with the types of tests. I think I got another hour in me to do it because now we're going to move on to our next test. I'm going to maybe spice up these videos here. But for the next test, what do we have? Our next test that we want to talk about here is a one sample means test, one sample t-test. So let's go right here and do one sample t-test. And this, we'll put a note here, quantitative. So it's one sample, meaning one variable. It's a quantitative test, so we're going to test one mean. That's what we got going on. The first thing we did was we talked about when to use it. And let's see just how we wrote that last one so we can be very consistent in our notes on how we're talking about this. When to use. We read we have one category variable we're testing to person a certain level. Yes. So when to use the one sample t-test. Let's do it. When to use. Okay, when do we use it? When we are testing one quantitative variable and seeing if the mean is equal to a certain value. Let's say hypothesize, that sounds better. A hypothesized, okay. So we're gonna test a quantitative variable, such as like age, weight, height, I can't think of other ones. I don't know why I can think of 1,000 ones. How fast you can run a mile. All these variables right here. Anything that's quantitative. How many times do you eat out a week? How much money do you have in your bank account? Let's just do all those things right there. Any sort of quantitative variable can be tested to see if the mean of that variable is equal to a certain amount. We can test of the mean of the amount of money students have in their bank account. We can test the mean amount of time students eat out a week. It just has to be a quantitative variable. So you have to ask, like, how many times do you eat out a week? How tall are you? How high is your GPA? It's weird to say it. Usually people say, what is your GPA? But it's like, how many GPA points do you have? Because it's a quantitative number. It's actual real numbers. That's what we mean by quantitative. You have to know when to use this, or else you might use the wrong test. So it would be like, let's see if students have more than $1,000 in their bank account. So we could do that test right here. We could see maybe, let's see here. Let's do the $1,000 in the bank account. Let's see, we go out and we talk to students and see if they have more than $1,000 in their bank account. Okay, so we need first the notation that we're gonna use for all this. So let's write our notation thing and make sure we have all the notation. Notation. The first thing we probably want to talk about is y bar. So we're going to need to insert some equation stuff right here. Let's go to insert equation and put in a y bar. Which one of these is the bar? There we go, y bar. Y bar is the what? That is the sample mean. So y bar is the sample mean. You know, we didn't start with our favorite one. I'm sorry. We should start with our favorite one, which is the easy one everyone knows. It's lowercase n for sample size. Sample size right here. We know what sample size is. We got it. So we got sample size and sample mean. Now we also need another sample thing. If we have a mean, we have a standard deviation. So this is sample standard deviation. It's like, hey everybody, sample standard deviation. We have that right there. Next but not least, we have mu naught. Oh, we gotta get some symbols again. Let's go back to our insert equation and put in here mu naught. So we need mu and naught. And mu is going to be over here, I believe. Yes, we found the mu. Nope, we don't want the mu there. We want the mu here. And so mu and naught. There we go. Hopefully I don't forget any of the notation that we need. This is the hypothesized. If you notice the theme of this, anytime we put that little naught right there, that little O, that is the hypothesized value we're going to say the mean is. So mu naught is the hypothesized true mean. And you could say hypothesized population mean. It's just like, okay, I'm going to say that it is true that students have $1,000 in their bank account. That's just what I'm hypothesizing is true. Then we're going to test that. So that's also the tested value. Oh, I'm sorry, I just figured I'd hop online and help you guys out. This will be a video review in advance. So this is just reviewing how to do the tests. Ask questions if you got them in the chat. And I think that's the whole equation. We've done all the notation. We know when to use this now, and we're just doing every single test. And now we need a fake question. So let's do here, example question. Example question. That's good. This is recorded, so definitely we got this. Example question right here, we will say, we go out and talk to 200 UT students. Classic sample size. and ask them how much money. It's a very personal question to be asking people. Apparently, we're just going out. Hopefully, there's no sample bias or response bias or non-response bias, but we'll ignore the possible biases that would probably go into asking a question like this. So this is just a hypothetical, theoretical problem, and let's give it a shot here. From here, let's see here. $2. Oh no. In the sample, it is. Let's say this. The distribution is very. Let's say right skew with a mean of, I'm trying to think of the math as we do this. I'm working the math in my head. Okay, I got it. 1,000, there we go. Let's do that. And a standard deviation of, I'm literally trying to solve this as we do this to see if I can get us to some pretty decent values. Okay, so let's do this. Let's say a standard deviation of 700. Cool, this will be pretty interesting. I think this should turn out to a t of like, I'm trying to do it in my head, but I think it's gonna be a t of about, my brain is slowing down today. It's gonna be a very small t, we'll be good. It'll be a small t. Hey, what's up, Andrew? Good to see everyone here. So now we have all the values I've been mentioning previously. Is there evidence to suggest that UT students have $1,000 on average in their bank account? Let's change the wording a little bit. Is there evidence to suggest that the true mean of students' bank accounts is equal or not equal to? There we go. I like this. Okay, so usually we want to word this for the alternative. There it is. It should have an apostrophe at the end of that. I can't grammar. So, because students have bank accounts. There we go. So the standard deviation is so big, yes, but remember, we actually need, and we should add an extra notation right here, we actually need the standard error of, and I'm going to need the little thing right here, a notation thing that we should possibly know. I'm going to have to do it as a thing. So we go to insert, equation, and we remember these little things as we do it. Let's go first one. There we go. SE y bar. So what is SE y bar? That is equal to the standard error of the sample mean, which is S over square root of n. That is S over square root of n, so let's insert an equation here. This is solved by the equation S over square root of n. Oops. So remember, we're doing S over square root of n right now, and you'll see this in the equation in just a moment here. But this is the standard error of the sample mean, and that's all that good stuff right here. There, we got it. We have all of our notation. We're pretty good to go. If you notice, I'm trying to write out everything you would need to know for this. And so we just have an example problem right here. We have the notation we're going to be using for this problem. So hopefully we can identify it. I'm going to try to mention the conditions this time. Conditions are kind of their own thing. They're very important, but checking them is usually just kind of rote once we get used to doing these problems. So let's give it a shot right here and see if we can identify the notation in this problem. So pause the screen if you want and see if you can identify all the notation I've listed out right here. So we have right here, 200 is the sample size, kind of classic sample size for all these problems we'll probably be doing today. Let's hop over here to where we can write 200 on the screen. And so we go and we write 200 is equal to n. That is the sample size. And then we have right here the mean is equal to this. Well, that is the sample mean because that came from a sample. So that is from my sample because that's from the 200 students. I also mentioned that the distribution is right skewed. That'll come into play. And I hope you can see there's a bar above that y. That is y bar. It's not just y. Y would be an observation, but y bar is the mean for the y variable. So anytime you put a bar above it, x bar is mean of variable x, y bar is mean of variable y. You could do t bar, mean of variable named t. So a standard deviation of 700, that's going to be s, little lowercase s right there, the best I can draw. And then we want to see if the value of the bank accounts is equal to 1,000. That is the hypothesized amount right there. We can do a little better mu than that. There is our mu. There we go. So we have the different values. But watch this. We can get the standard error. The standard error is going to be s over square root of n. So we need to do 700 over square root of 200. And 700 over square root of 200 is going to be 200 square root. You have to do it this way on this calculator. Where did we lose our thing to? And now 700 over square root of this, 49. Cool. I like that. That's going to be, now I can already tell you the z-score. The z-score is almost exactly, it's about 0.61, I believe. The z-score is 0.61. You'll see that here in just a little bit. If you are following along really well, you'll be like, I see how he did that, because I actually just solved most of the equation. I will tell you more on that in a moment. 0.4950. The next two digits round up because it's 497. So with this in mind, we have the standard error. So this is the standard error of y bar. And we can use that here in a moment. But we've taken and we've done all the notation. So now we need to go and we need to grab our steps. Let's go back all the way to the top, make sure we have all of the steps. So let's take our 4 steps and let's practice. You ready? Big brain. Okay, let's do all the steps right here. Okay, so write out the null and alternative hypotheses. Write out the null and alternative hypotheses. Okay, we are testing the mean. Always look at these equations and see what it says we're testing. It says, is there evidence to suggest that the true mean, I know I'm looking at mu now, of students' bank accounts is not equal to this right here. So I have not equals to. That's telling me the alternative right there. So all these things I've highlighted are very important for what we're solving. And I've kind of boiled these problems down to where there's no like fake info, I hate those problems. Yep, we have mu right there. Good job. The null hypothesis is that the true mean is equal to it, and you got it. Perfect answer in the chat. Great job. We have here the null states that the true mean of students' bank accounts is equal to $1,000. The alternative states that the true mean of students' bank accounts is equal to, oh my gosh, not equal to, there we go. I was back doing the null again in my head. There we go, we've got the null, we've got the alternative. The null states that the true mean of bank accounts is equal to 1,000, great job in the chat. And the alternative states that the true mean of students' bank accounts is not equal to. Please do not make this error, which I often see. One, I see this error a lot of times. I see where people just write this, the null states equals 1,000. Make sure to tell me what equals 1,000, the true mean of money in students' bank accounts. Make sure to not make this mistake. A proportion can't be $1,000 because a proportion is a value contained between 0 and 1. So if you write proportion, be like, that's a problem. Question in the chat? Any questions, feel free to ask them as we walk through all of these steps right here. But we have here, this would be a mistake. Let's make sure we know that we want to do the true mean is equal to 1,000. And the alternative would be the true mean is equal the true mean is not equal to. Awesome. And I hope this helps. I hope this helps everyone out. I want these videos, I might chop them up a little bit, but I want everyone to be able to watch these and to be able to understand how to do each step. So this is out to all Stats 1 students, so that way you can practice doing this and know when to use each test. So I'm going to do the next 2 after this. So perform the calculations for the z, the t, or the chi-squareds. Also check conditions. My students should know condition 1, and right then they say random. That means we randomly selected these, and I might not have said that in my problem. 200, let's just fix that. It's not going to move it. It didn't move it. So mine would fail the condition because I didn't say it was random. So make sure your problem states that they're random. We should talk to random people. You don't want to just go talk to the first 200 people. That would be a convenience sample. So oops. And if on the test it doesn't say random, probably means you failed the condition. We're usually more careful. These are just questions off the top of my head. But we would not pass the randomness condition here because the question does not state that they are randomly selected. I would probably say that on the test. Like, the question does not state the students are randomly selected, so that seems to be an issue, and we do not know for certain they're randomly selected. This is a problem with the test. Condition 2. Condition 2 is 10%, as in we need to select less than 10% of the population. So it's pretty clear that 200 students is less than 10% of all UT. UT has something like, I think, I'm going to probably quote a wrong number, 20,000 undergrad, let's just say that. And I know we have more than 2,000 undergrad, so 200 is way less than 10% of all UT students. So 200 is less than 10% of all UT students, we pass. And then the last condition for this is nearly normal. If you notice, I highlighted that the distribution is skewed to the right. That's because there's probably some students with very large bank accounts like this. So you could say 1,000 is here, or I'm trying to think where 1,000 would be at. It'd probably be over here because it's a right skew distribution, or maybe a little further over. But wherever it is at, it does have a right skew to it. We see that the distribution is skewed to the right. There's a lot of people with lower bank accounts, and then there's this heavy right skew where we see some students with very, very high bank accounts. So with that in mind, do we pass the nearly normal condition? The answer is yes, we do. Because although the original distribution is skewed to the right, it could look something like this right here. The distribution of the mean will be normal, more normal, and tighter the larger n gets. So that blue distribution I've drawn right there is the distribution of the mean, and of sample size of 200 should be large enough that the distribution of the mean will be more normal and tighter and nearly normal enough. We're not concerned so much of the first distribution I drew, the black one in the background. We're concerned about the distribution of the mean, which will actually follow the rules of the central limit theorem, that it'll be more normal and tighter. And you know, if you remember back how it gets tighter, it's by n. As n gets larger, that gets smaller. That's it getting tighter right there by the standard error. And then the more normal is when I draw the blue distribution looking more normal. So it's not that the black distribution ever becomes normal, it's that the distribution of the mean should be nearly normal. So all that key stuff right there. We do seem to pass the nearly normal condition because 200 is large enough to make the distribution of the mean be nearly normal, even though this is right skewed. So we pass all our conditions. Now we just have to know the equation, but great stuff for us. We don't have to know it, it'll be given to us. So let's go ahead and write out the equation. Let's go to Insert, Equation, and we're going to solve for t with n minus 1 degrees of freedom. T with n minus 1. We won't need the pen for a little bit here. So let's go to Equation. We're an equation builder, aren't we? We are. Where'd my equation go? Insert, there we are. Equation, can't do an equation inside equation. Okay, so we need t with n minus 1 degrees of freedom. Okay, there we go. T with n minus 1 degrees of freedom. That subscript right there is the degrees of freedom. And now we're going to go equals, and after the equals, we're going to put our equation. So let's go right here and put the bottom part of it, which is going to be s over square root of n. So we need to first do this. And let's go here, and let's do that. And s over square root of n, if you notice I solved that earlier, and this will be y bar minus mu naught, so we need a little y bar right here. Let's put our y bar, which is the sample mean, minus mu naught, which is the hypothesized mean, the hypothesized true mean technically. So we're going to put a mu naught right here. There's the mu, there's the naught, and we got it. We have now written our equation, and once we click outside of here and click over, it's going to make it small. But we're going to copy paste this equation, put them side by side, and show how the equation is solved. Now, please note, I already kind of did some of the work for this, because since the problem gave it to me, I went ahead and solved for the standard error. The standard error was 49.50. And if you're wondering how I did that, it was just s over square root of n, which we saw previously was 700 over the square root of 200. That is s, which is the standard deviation, over the square root of the sample size. So 700, which will be right here, over square root of 200 equals to 49.50. Now I'm simply going to take the difference between the two. The difference between the two is going to be 1030, which is my observed sample mean, observation minus mean of what we would expect. And if you notice, the difference is 30. This was the math I was doing in my head earlier in the question. I said, what's 30 divided by 50? Oh, that's 0.6. Well, because it's 49.50, it's going to be about I believe I said 0.61. Let's see how close I was with my guesstimate of this. Well, there's our standard deviation. Let's carry all decimal place accuracy with it. And Brian said it would be, it's 30, I knew that. But let's see, I said 0.61, the answer is and it rounds to 0.61. We did it. It's 0.606, but it rounds to 0.61. So you know what? I'm taking the win on that. I'm going here and I'm writing 0.61. That's what I said it would be, and what is this n minus 1? Those are the degrees of freedom. So let's add in the degrees of freedom here. That is a t-statistic with 199 degrees of freedom. That is a subscript. Do not multiply those numbers. Stop, don't multiply those numbers. That is a subscript, and you might just delete that off now so there's no confusion. So it is equal to 0.61, but there are 199 degrees of freedom. So you know what? We forgot one thing on our notation. Our last thing on the notation should be df equals degrees of freedom. And that is n minus 1. Every t will have with it degrees of freedom. I forgot those degrees of freedom in our notation. So sorry if you've been going down through the problem, but these are all the notations right here, and now I've moved the text. But the degrees of freedom, df stands for degrees of freedom, and for this test it is n minus 1. Watch out, let's put a note. For this test, let's put an exclamation point right there. Only for this test, the one sample t-test is n minus 1 degrees of freedom. Very important stuff right there, and oh no, we're gonna make the notes all crazy if we leave this in, so we can't. Let's do this. Let's go down here and write out that down here. Okay, so let's put it right here, make this look all nice, and let's go df equals degrees of freedom n minus 1, and then put a star for this test. Only for this test is it n minus 1. And why? It's a one sample t-test, and there's a lot of theory behind it. I'm not going to do that right now, but I can tell you why. It's because of the estimates for the mean, but we won't go into that right now. But for your knowledge, a one sample t-test has how many degrees of freedom? N minus 1. A one sample t-test has n minus 1 degrees of freedom. Nice and easy to remember that one. Find the p-value. Well, we got the t-statistic. Here's the thing. We can't know this exactly, but I can give you a pretty good guess of it. And this one I'm going to be pretty good on the guess on the p-value. Here's what we got. Is we've got our curve. And with enough degrees of freedom, people in my class might know, with enough degrees of freedom, the t is basically the what? With enough degrees of freedom, the t is basically the what? And what is enough degrees of freedom? Usually about 60. The t is basically the z. The t is basically the z. So it's never exactly the z. The t, we talked about it earlier, becomes more like the z. Remember, Mr. T comes in and says, "Pvalue," smashes it down, and then it rises back up. It's probably the worst Mr. T impression ever. I still want to make videos with him. If he's ever like, "Hey, I want to make some stats," I was like, "Yes, dream come true." But, because we all love him in statistics for his t distribution. But it's basically the normal. It's a more exact calculation created by William Gossett, who Ronald Fisher wouldn't publish his work, and so he used the pseudonym student T to get the t distribution published. So it's a more exact curve that takes into account smaller sample sizes based on the degrees of freedom, and standard deviations and other stuff for other tests like two sample t-tests. This one only takes into account sample size. So what do we have going on right here? We need to find the p-value. That's the whole goal of this. We need to find the p-value by plotting it. Now this one's going to be tricky. How are we going to find this p-value? Step 3, find the p-value. Well, I need to plot that, okay? Okay, so I'm going to go here. I'm going to plot right here at 0.61. Now be careful. You're almost done. When you do this, make sure to shade according to the alternative. What way am I going to shade? What way will I shade my alternative? I'll shade my alternative. This points to the right, and that points to the left. So I'll shade both sides. I'll shade both sides. That's what I'll do because it's the two-sided test. This is the does not equals test. So I'm going to draw a line right here that is just as extreme on the other side at negative 0.61. So because the alternative is a two-sided, if it was one-sided, I would just shade to the right that way. If it was left, I would shade to the left, less than. But since it's two-sided, I shade to both sides. So we go here and we shade our p-value. And I know you might be thinking, I can't figure out that p-value. Does it look like I've shaded more than 5% of the curve? These are the kinds of test questions we really like here because the program will tell you the exact p-value. And I'm going to try to take a good guess at this here in a moment. Oh, why not? I'm going to guess that this p-value is 0.57. That's my guess of the p-value. 0.572. 0.572. And I'll tell you if I got close how I knew. Oh, no, wait. Oh, I can't. No, I'm going to guess 0.18. That's a 1 right there. I swear the video is not edited. 0.518. And I'm trying to think. Maybe statisticians watching this be like, I know why he's guessing that. There's some numbers, and I can't for the life of me think up the one number, but let's find out the p-value. I can no longer use the z-curve. I'm not using the z, I'm using the t, and it looks virtually identical. You'll notice things about this that as you increase the degrees of freedom, you're basically getting the z-score, but when you decrease it, it starts to get smashed down. Smash down, rise up into the normal. The more degrees of freedom, the more availability it has to be normal. So what did we get? We got a t of 0.61. We're not done though, because we have to put in our degrees of freedom. Oh, sorry, that's degrees of freedom. Degrees of freedom were 199 because the sample size was 200. We got a t-score of 0.61. And what is our p-value? Oh, it's close. I was thinking of the interquartile range z-score, so don't worry about that. Little side note of why I was guessing it. I should have went with my other guesses. I think I had some guesses closer to that. But the p-value is 0.543. But I want you to look at that graphic, and I want you to look at my graphic. So I want you to think, how similar does my graphic look to this one? It doesn't look perfectly like it, but it looks a lot like it. And I think it was 0.543, so let's put in the exact p-value right here. I didn't know when I made up this problem that it would come out to almost that score, but that was kind of nice. And so that, I believe, we'll double check the value because we want to be exact. We want to put the real p-value, not close to it. Yep, 0.543. That is the area shaded outside the curve. That is the area under this curve here on the right and to the left of it, below negative 0.61 and above positive 0.61. If I shade to the right, what would the p-value be? Well, maybe this could be a test question. All you would do for the right-tailed test is take this right here and do what to it to just get the greater than test? Take this and divide it by 2. 0.272 if it rounds. Let's see what it rounds to. 0.272. And it rounded down. There might be some decimals we're not seeing, but if you notice the two-tailed test is simply double, and there's just some decimals we're probably not seeing, or it's annotating decimals because there might be a 5 after that. But it's just half of it. How about if I go below this? What should the area be below that line? Well, this is good practice. The area below that would be 1 minus that area. So that will be 0.72, and let's see if it says 9 or 8. It'll be one of those two. 0.729, so that one rounds up to 0.729. So all that's going on right here is we're just seeing how the different p-values are calculated. This is the less than test because it shades below where we landed. This is the greater than test because it shades above where we landed. And this is the two-tailed test because it reflects the area on the other side where we landed. So make sure you know that when you have a greater than test, you shade to the right. When you have a less than test, you shade to the left. And when you have a two-tailed test, you reflect the smaller area on both sides. P-values can only be between 0 and 1. If you get one bigger than 1, you've done something wrong. Well, we're basically done with the problem. I've got the p-value, and if we gave this to you on a test, you might say, wait, I can't figure it out. That's definitely more than 50% or 0.5% of the curve shade, or 5%, excuse me. That's definitely more than 5% of the curve shade. That is a very large p-value. Either way, just when you draw it out there and you look at it, that is a very large p-value. So what do? Well, we just need to state our conclusion. We are going to say, I fail to reject the null. I fail to reject the null that the true mean of student bank accounts, I did it again, I don't know how to grammar, is equal to, this means I did not have evidence the true mean of students' bank accounts, we're going for all the points on the test, is not equal to. What does this actually mean? Like, what are we stats people saying with this? It just means it's believable that the true mean is $1,000. And that's not an individual student having $1,000. It's like on average, students have $1,000. Apparently, due to this fake problem right here, it's a believable claim because we did not land far enough away. Think about what kind of evidence would lead us to rejecting the null. What if I spoke to these 200 students and they had on average $50,000 in their bank accounts? You might be like, that sounds like good evidence. What if they had exactly 1,000 as their mean? Well, then we'd land right here again, and that would lead to the highest p-value. In this instance, if we landed there on the two-tailed test, the p-value would be 1 telling us that is the most likely thing to see if the null is true. And just think about that. The most likely thing to see if the null is true is $1,000. And if we landed there, we would say, well, yeah, I guess the null is pretty believable. We're not saying the null is true. Do not use those bad A words. Do not say that except word. Don't say that. We would just say, I continue to believe the null, or I do not reject the null. I fail to reject the null. So continuing to believe is fine. We're not going to state the null is true. We're not going to say we've proven anything. We're just going to say we have evidence for the alternative, or we did not find evidence. Very big stuff on the wording right there that you're hearing me use. You won't hear me, hopefully, say words like I've proven this, or I know this. In statistics, we're science-based, so we say I have evidence, or I did not find evidence. So that's what we have going right there. And you should know which of the claims is the evidence-based. The alternative is the evidence-based. The null can be anything. We start out with a null, we test it, and then we see if we have evidence for the alternative, which would lead us to reject the null. If there's evidence for the alternative, we reject the null. If we don't have evidence for the alternative, it's because we cannot reject the null. That is 2 out of the 4 done. Let's see, we got more energy. Need Red Bull to come out here and give us more Red Bull. 2 more tests to go, and then we're done. Then it's fall break. Fall break, it's not fall break. It is Thanksgiving break. That's what's going on. 2 more tests to go. Let's do this. So the second to last test today is going to be, let's do this. Here we go, home, and let's do it. I gotta remember the quick key. I think it's Control-C for that. No, Control-E, that's a weird one to center the text. So we have here the 2 sample t-tests. Put a dash between those. 2 sample t-tests. We need to know when to use this. When do we use the 2 sample t-test? So when to use? When data collected will be a quantitative y and a categorical 2-level x. I think that's basically it. We often test to see if the difference between them is 0. Okay. So what do we have going on right here? What does this all mean? A quantitative y. Like we could test the heights of people. We could test the heights of males and females, the heights of juniors versus seniors. We just have to pick 2 levels of the variable. So we have to do things like, let's test the heights of juniors in college versus seniors in college. Someone says, you know, I think seniors are actually taller than juniors. We'll do that right here. We're going to test the heights of juniors versus seniors. If you notice, we have 2 levels to a categorical variable. And then we have a quantitative y, like height. So we need to collect data from both groups. And so the notation here is going to get a little bit interesting because there's going to be a lot of repeat notation. And so let's take a look at this right here. So we have our notation. Notation is going to be, let's start off with classic, and we got n. But now it's not just n. We don't want to do just n. We want to do n1 and n2. So let's go into here and drop in notation n1, and we need n2. So n1 is sample size of group 1. That is n1, and then we have n2. That is going to be sample size of, you guessed it, you know what it's going to be, sample size of group 2. And we can use this, we can cheat. Watch this. Oh, I shouldn't, wait, watch this. We're going to copy paste. We will also have S1 and S2. Because now we need not a sample size of each group, but a sample standard deviation. And let's go right here. Sometimes you'll lose the cursor on these screens. Oh no, there you are. Standard deviation. There we go, standard deviation of group 1, standard deviation of group 2. And if we have, look at this, if we have sample sizes and we have sample standard deviations, we probably need, if you look what I'm going to go get, we need a sample mean. So if you look at that right there, we've got our sample mean. Let's go down here and put that notation just for us. It's very similar to the 1 sample means test, but now we're doing 2 sample means. And so we're going to go in here and we're going to grab these notations. And we're just going to copy paste just to literally show these are the same concepts that we are doing. It's just slightly changing with what we have. Let's delete the S, so it doesn't like that, so then let's not do that. Let's go back in here to the insert. Let's go to equation and let's drop in our y bar. There's the bar. We'll change in a moment here, but this is going to be the sample mean of group 2. And this one right here is going to be the sample mean of group 1. You're right. So we need to remove these standard deviations off the way. And we're almost done. We could probably, we got a little, I'll mention these as I go through. I'm trying to think what else we need. Degrees of freedom. DF is degrees of freedom. Complicated formula. We'll use an applet to solve it. It's a complicated formula, and I'll go ahead and show it to you. So let me pull it up here. Let me pull up the 2 sample degrees of freedom formula. 2 sample degrees of freedom, t-test degrees of freedom formula. And let's pull a picture of it just so you can see what we're actually solving. And the formula we are solving is this nice. I think I can copy it. Let's copy image. And let's bring it down here so you can see it. You will not be solving this. So let's bring it right into here. I should have it copied. Let's cross our fingers. The answer is, there it is right there. That is the formula that you're actually solving when you go to our site that lets you solve this. Oh my gosh, it took over the page. Go away. We don't want you here. So we will not be solving this. We will not be solving that equation. That could just be like, solve this equation on the test. That's not what we're not here to do. If you notice, it's based on standard deviations. It's based on sample size. This test right here uses a complicated formula. You will not be solving it, so do not worry about it. The degrees of freedom just tell you what t you are using. So you can see it again. What do you do with the degrees of freedom? You bring that over to your t applet, and in the t applet you enter in the degrees of freedom. If the degrees of freedom are small, the t is smashed down. If the degrees of freedom get higher, the t rises up. Eventually the t basically rises up into the normal curve, kind of. It technically takes infinite degrees of freedom, but after about 60 it's kind of similar, because watch this. If you remember the classic 68, 95, 99.7, 95 with 60 degrees of freedom is a t-score of 2. 68 is a t-score of almost 1. 99.7 is not quite 3, so the curve gets a little different. That's why we don't always just use all the calculations. But look, 68 is basically 1 standard deviation, or standard error for this curve technically, and 95 is almost exactly 2 down to the decimals. But the reason is, as it gets more freedom, it'll get more normal. Notice the very small change when I go from 60 to 600. The curve will rise up a little bit more. Did you see it? See it go down, up, down. Watch it go way down, down, up, up, up. It's really hard to notice the small changes, and you might notice that the t-score, is actually the z-score. That's why I said it in my mind, that the t-score right now is basically the z-score. And I say basically because there's additional decimals for the z-score we're not seeing in the t-score, because there's small decimal differences we don't see. The t never becomes the z unless it has infinite degrees of freedom, but it becomes basically like the z. So you can consider a lot of your t's to be basically z's, but with small sample sizes, watch out. That's where you see your drastic differences. So anyone watching this in the future, if the sample size is really small, you'll see drastic differences between the t and the z. The t is going to have more of a pushed out. It's going to be harder to reject and make wider confidence intervals. So the t is basically the normal, but it's more exact based on our uncertainty due to a smaller sample size and the standard deviations in the calculations. William Gossett made some big impacts in statistics with that right there. So we got a little bit of a review right there. What are the degrees of freedom? And I'm thinking through everything we have in the equation, and I think we've got it. That's got it. So let's take a look. Now we need an example problem. Whew, got a lot of notation on this one. Example problem. How many people do we have watching? I'm wondering. I'm going to cheat and I'm going to look. The answer is, oh no, where's my watching people page? The answer is 4 people watching. Yay, I'll take 4. Okay, sorry, I interrupted the video for that. Okay, I just wanted to see. I was hoping there'd be at least a few. Okay, cool. So we have here an example problem. And I'm hoping these videos get used a lot for practice for the test. That's why I'm doing this. I'm going to do a few more like this to help people practice and see a few example problems. Because everyone's like, Brian, I want to see more problems. I want to see more problems. Well, you got it, more problems. So example problem. We go and collect 200 random UT students. 100 of the students, of these students, 100 are freshmen. Sure, let's do freshmen and seniors. Freshmen and 100 are seniors. You do not have to have the same sample size, so let's not do that, I guess. Let's go 80 and let's go 120. I just don't want people to think you have to have the exact same sample size. It's easier to make the math that way, but it doesn't have to be. So what did I just give you right there? You notice I'm giving you N1 and N2. And then let's say here, seniors are normally distributed in their heights with a mean of 70 inches. We're doing males and females, so let's do 68 inches. 68 inches and a standard deviation of 4. I guess we'll pretend it's normal. I'm going to say in the problem it's normal. And if you look at what we're going to do, we're going to cheat because we're going to copy paste this because we're basically writing the same thing but for freshmen. So freshmen are normally distributed with a mean height of 67.5. I'm going to make the standard deviations equal. And is there evidence that freshmen, let's do that. Freshmen are shorter than seniors. If you notice what I've done today is I've done all the sidedness to the test. And I kind of want to put this all on its own page. So I'm going to make it a tiny bit tinier. Cool. That's got it. So it's all on its own page. Is there evidence that freshmen are shorter? I think that's grammatically correct. Is there evidence that freshmen are shorter than seniors? Okay, we got to grab our 4 ways to do the test. Got to go back to our 4 ways to do the test. And let's go right here, grab those 4 steps. We reviewed those at the start. Let's bring it all the way back down here. Let's drop in those 4 steps, and we got it. Here we go. Write that null, write that alternative. Let's do it. For this null and alternative, we are testing the difference between the 2 means. So we need to write a null here that states that the true difference between the means is equal to 0. We're going to see if freshmen are shorter than seniors. So let's think about that. That's going to be a minus. Let's check it out. The null states that the true difference between freshmen's means and seniors' means. Does everyone see I've written the null states that the true difference between freshman means and seniors' means is equal to 0. The alternative states that the true difference between freshmen's means and seniors' means is less than 0. Actually, and I reversed it. Let me change this. I'm going to go back in time here because I actually want it to be the negative sign, and that would actually be positive. The way I want to write it is the following. We're going to put here mu senior, and I'll explain why. Mu senior minus mu freshman is equal to 0. And we're going to put the alternative states that mu senior minus mu freshman is less than 0. There we go. I'd have to reverse my sign, and I'll explain what's going on right here. If you think about the mathematics on this, the mathematics would state that if you had something like freshmen are, oh my gosh, I am reversing the signs. I'm sorry, guys. It's later in the day. You know, you should always go with your first answer. Let me double think about this. Mu freshman minus mu senior. If seniors are taller, it'll be negative, correct? There we go. It's very easy to reverse these. There we go. Also, mathematically, I want you to think about this. Here's another way to check that you did it correctly. Flip the sides of it, put seniors on the other side, and you could actually write this technically mu freshman less than mu senior. So this is another way of writing it right here. You could technically write these the following way. They are mathematically equal. They just don't follow the same structure. So if you do get confused like I just did, if you're doing a problem on the fly, you might look, does it make sense the way I've written it? Does everyone see kind of how I can transpose it to say the mean of freshmen is less than the mean of seniors? And that's where I have mu freshman minus mu senior is less than 0. So I double guessed myself and I was correct the first time, just going off of the way of doing it. When we take that difference, it would be negative. If you also want one last check, are you like, I don't know, I'm still thinking, did I get it right? Go here and put in a number like, let's do it. Let's put in 60 and let's put in 70. 60 minus 70 would be less than 0. That would lead to evidence. So if we're testing to see this, we'd want to see a negative difference right here, which is kind of where our problem is set up. And I don't know if we'll find a difference. This one might be an interesting t-score. We'll have to see what the standard error is. So we got all this right here. And let's give it a shot. Let's click over here on our text button and put in new text. The 4 conditions, and we're not going to focus so much on conditions today, we're going to focus on more about doing the mathematics. Conditions are more written portions of the task, but you should always check conditions. They're majorly important. I'm not downplaying conditions, but the conditions are random, we took a random sample, 10%, we take less than 10% of all UT students. Condition 3, nearly normal, the test stated, or my question stated, that both distributions were normal. So the distributions of the means for them should be nearly normal. Number 4 is what? There's a 4th condition for independent means. And the condition is the means are independent. So you have to ask yourself, do you think seniors' heights influence freshmen heights? And the answer is no. Seniors' heights, like it's not like seniors are tall and freshmen are like, ooh, seniors are tall, we should be tall too. These are independent means. It's a non-paired test. So with the independent means, we can say that we meet the independent means, that seniors' heights is not dependent on freshman heights or vice versa. So these are independent means. So now we just have to calculate the t. Well, here's what I'm going to do. This t is very similar to the last problem I wrote. So I'm going to go ahead and grab this equation right here and use it to solve out this t equation. We're going to augment it and you're going to see how similar it is. So what we need at the top of this is we need now y bar 1 minus y bar 2. Can I take these? It never lets me copy paste between these. There it goes. Y bar 1 minus y bar 2. What's interesting, in truth, if we were to look at this the way it's primarily written, and we'll put down here degrees of freedom because that's the complicated form for the degrees of freedom, and we need a 2 on that y bar. So the top of this equation right now is the difference between the 2 sample means. In truth, this is the observed difference. So this is actually the first thing you're calculating here. This is what we observe. So if you've been watching the other videos, this is what we observe, and that is what we expect. We expect the difference to be 0, and that's what we're testing against. If you notice that value I have up there, that is the hypothesized value, and that's what always goes over here in this spot. You can see that in all the other tests I've been doing, the hypothesized value goes right here, and since we hypothesized the difference is 0, according to null, we said, I believe the difference is 0, so since we believe the difference is 0, that goes here. Now you don't have to write that because you're just subtracting 0, but just theoretically, or kind of how it works, that's what you're doing. You can use other values as a null value, so in other tests you can use a different value. So let's put in our remainder, which is the standard error of the difference between the means. So maybe we'll write a side note down here that this is the standard error of the difference between the sample means, and let's add it in. We're almost done, got almost all the spots we need on this. Oh no, we jumped out of the thing. Is that not? Oh, I think I just have to put it in the thing. Let's do the thing. No! Okay, we gotta do it the hard way. All right, let's put this. Let's go here. No, don't do that. Oh, really? I have to do it here? Oh, well, I should have done that. And then let's go here. Let's grab the whole thing. Let's square root it. And then let's go to this one. Let's put it in an exponent. And let's put it in an exponent. Oh, we need the double. This one needs double, and this one needs double. You might think about what we're going to be putting in here. You don't have to memorize these equations. These equations will be given to you on all of our tests. So what do we have right here? If you look at the similarities between what I just had pasted, it is going to be S1 squared over N1 S2 squared. I should have put that squared in when I had a chance, or 2 over N wait, don't go there. Go there. N2. There we go. It's basically S over square root of n, but it has with it the kind of grouping of the two. So we have both standard deviations and both sample sizes right here. We're kind of adding them together, but you can't just square stuff because S squared and n squared, because it was n square root to begin with, we can't just square it. Since we're adding them up, we're going to unsquare root them after we're done. So we're basically putting the two standard deviations together, standard errors, and what do we get? This is actually right here. Let's make it very clear that this is the standard error. This bottom of this equation, I'm going to circle it. This thing right here, that is the standard error of y bar 1 minus y bar 2. Can't write today. That is the standard error of y bar 1 minus y bar 2. That's subscript right there, but that whole thing is just the standard error of y bar 1 minus y bar 2. You might see that in jump output saying standard error of the difference between the two means, because y bar 1 minus y bar 2 is the difference between the two means, and that's got the equation. From here, it's just solving mathematics. Look at this. We are almost done with another example problem. Yes. And I hope this helps a lot of people out. Remember, you can always email me and request videos, bs@utk.edu, bstevens@utk.edu. Either one of those works. Email with questions or video ideas. Let's put in both of these right here and give it a shot. Okay. Woo! Got a lot to fill out. I think I can kind of remember a lot of these answers for what we put in. We have here the difference between the two means. We're doing freshman minus senior. So we're going to knock off this 0 to begin with because that 0 doesn't matter. And then we're going to go here and we are going to put in sample mean 1 is equal to, this is the freshman's mean was 67.5 and sample mean 2 is equal to 68. That's a difference of 0.5 on the top or negative 0.5. Then the standard deviation on the bottom, I think they were both 4. And it doesn't matter, well, I guess, did we sample more freshmen or seniors? How many freshmen? I think we got 80. In truth, it won't matter because the standard deviations are the same, but you know, it's nice to keep your notation nice and neat. And then this is sample size 2, which should be our sample of seniors. This is the standard deviation. Oh, and I lost, oh, there's the square. We need the square. So we will have to add in a new notation here, just so we can see the mathematics as we've done this. Please try to solve these out on your own. Just very good practice to solve these all. And know that you can do these on the test. So that's 4 squared, and that's 4 squared, which is 16. And man, if I'd kept those standard deviations the same, that would have been easier to do. And so let's take a look. We sampled 120 freshmen, so this right here should be 120. And this right here should be 80 technically. We're just going to make sure we have this technically correct. The mathematics would still work out the same because we had the same two, like 4 squared over 120 plus 4 squared over 180 over 80. Same mathematics, it would have worked out the same way. So it wouldn't have caused a problem, but now it's just technically correct with the sample size of freshmen underneath the freshman mean, which is 67.5. So let's continue on. We need to solve for this t-statistic, which I'm going to do the mathematics for, and let's do it. 67.5 minus 68. The top of the equation, if you can't see it, is negative 0.5. The bottom of the equation is going to be the fun part. Well, it's 16 divided by 120. That is that. We're going to copy that for the moment. Then 16 divided by 80, which is 0.2. So then we add these two. Really? Oh, that's so cool. It's 1/3. And then when we square root 1/3, bada bing, bada boom, we get that right there. That's a weird one. So when we square root 1/3, we get this right here. So if we square that, we should get 1/3. Bring it back, square it, square root. Don't worry about that. Just so you can see what happened, this equation right here, let's just reduce it down a little bit further. Just so you can see it's 16. Over here, this is 16, and the top of the equation solves out to negative 0.50. That's because I subtracted those numbers, and then the bottom of this equation right now, when we solved it down here, turned out to be square root of 0.333. And all we're doing is just reducing this down so you can see the mathematics I went through. Make sure to rewind the video or rewatch just to see how I solved this. And once we get this, we've now square rooted that. Hopefully I've been solving everything correctly. And if you look, you can tell the t-score. It's going to be close to about negative 0.87 or something. So all we're going to do is take this number right here. Let's make it very clear. And that number, I don't have it in the paste. Oh my gosh, I do have it in the paste. There we go. So we're going to divide these two numbers to get the t-score. And the t-score is going to be negative because our difference was negative. So the top part, if it's negative. So all we're going to do is take this, what did I say, negative 0.87, divide by, and it's negative 0.866. I didn't add in the negative, we'll just remember to add that in now. Negative 0.866. And was it rounded up or rounded down? Because I was so close. Hey, it's 0.87, it is. Yeah, if you round it, wow, just look at that. If you round it up, it does that. Okay, so we have our t-score. We are so close. We are so close to being done. Well, we can draw this out again. Here's the thing. This t is more complicated. We need to find the degrees of freedom for it. So we're going to head over to Charlie Quick to help us out. So what we'll do is we'll go here and we will Google toSample, not down there, we'll Google it. toSample degrees of freedom calculator. It's actually the second one now. It used to be the first, but this is the one we generally use. I checked out the other one. I still like ours better. If you look, all we do is we enter in sample size of group 1, which was 120, sample size of group 2, which was 80, 4, and 4, and I'm going to guess the degrees of freedom are 194, 169. There we go right there. It is a complicated formula, but can't get them all right. So we're going to take those degrees of freedom, bring them all the way back to here, and put them in. And we basically have the normal curve again. Basically, but we need to use the t-curve. It's more exact. That's why we use it in statistics, because it takes into account the sample size and standard deviations for this one right here. So if you notice, my t-statistic was negative 0. I want to draw it first. 866. And we do a left tail. I didn't draw this one out first, but I could have. Just think about how, and I want you to practice this. I want you to practice drawing these. Because what would I do back here on my cheat sheet? I need to draw the alternative. Well, let's do it. What I do is I draw what looks like a t-curve. And t-curve basically looks normal. Then I go here and I put my number line a little bit better. And then I go here to 0, negative 1, negative 2, negative 3. Go up 1, 2, 3. Then I plot where I landed. I landed at a t-score of negative 0.866. Now, how do I plot my p-value? To the left. Why in the world am I plotting to the left of that? Why in the world am I plotting to the left? The reason I'm plotting to the left is because the alternative is the less than alternative. If you notice the direction of the sign, the alternative is the less than alternative. And from here, it's downhill. We just need to now write out our decision. Guess what? My p-value is high, so I do not reject the null. My p-value is, and let's look back what it was. We'll put it on our curve 2 here that we drew. 0.196. If you notice, that's the same curve as this right here. Basically identical. Not identical perfect, but close enough. So the p-value here, so p-value is equal to 0.196, telling us the probability of a result as extreme or lower than what we saw in our sample would occur about 19.6% of the time, given that there is no difference between the means. So this seems likely, given the null is true. If you also notice, although this is not a z, it's kind of similar, that below here would be 16%. That's because of the empirical rule. We would have 68% between here and here. So with 68% between, that would leave 32% on the outside, and so we basically have something a little bigger than 16% with that p-value of 19.6. So our p-value is a little bigger than what we could estimate via the empirical rule. We'd say it's probably a little bigger than 16, but it has to be less than 50. Lots of great practice on knowing how to reject or not to reject without using the applets. Pretty much it's easy to tell that that is a very large p-value. So my p-value is 0.196, which is larger than alpha of 0.05. That's the general alpha we assume. Because of this, sure, fix it. We will fail to reject the null hypothesis. We do not have evidence that there is a difference between the true mean of freshmen and senior heights. That's it. We do not have evidence of a difference. We don't reject the null. I continue to believe that they could be the same height. So on average, it looks like we would believe that freshmen and seniors are about the same height. We do not reject the null. We did not have evidence for that alternative. One more test. We got this. We got this. So one more test. Everyone ready? All 4 people ready? Let's do the last test here, which will be our last day of class. Oh my gosh, wait. We have 2 more days of class. Second to last day of class. So second to last day of class right here. Let's do it. Okay. So what is the last test we're doing here? Let's do it. The test is the chi-square test of independence. If I knew how to spell. Sure. Independence. I think I got it right. Perfect. Chi-square test of independence. I do math. I don't spell. When to use. When to use. We will use the chi-squared test of independence when we have 2 categorical variables. So if you kind of notice the theme of this, the first one was categorical, the second one was quantitative, the next one was quantitative categorical, and then this one is 2 categorical variables. We will use this test when we have 2 categorical variables and want to see if the variables are independent of each other or not. See, if you don't think about it, it's easier to type. If you start thinking, you're like, I don't know how words are spelled, you know what to do. Type in long enough. So what we have right here is we have 2 categorical variables. Maybe we want to see if freshmen like cats more than dogs, or versus seniors. I can't speak today. If freshmen or seniors like cats or dogs more. So we'd have to ask someone, are you a cat person or are you a dog person? And so that's one variable, cats, dogs. And then we have another variable, are you a freshman or are you a senior? Does everyone see that right there? This one's going to be a little bit complicated because this is our last lecture and the math is going to be a little bit bigger on this one to get the chi-squareds. But luckily, the questions are a little bit easier. So we have, and I'll give a different example here. We could see maybe, we always do like UT and Florida students. So we compare UT and Florida students and we ask them, do you think you'll go to a bowl game? So which school thinks that their school will go to a bowl game more? Does it depend on the school you go to or is it independent of the school you go to? And by dependent, that's the same thing as not. By dependent is not independent. So it's either independent or not independent, and not independent, let's put a side note right here, is the same as dependent. So is that clear right there that those things, independent, and not independent means dependent. But I like to say independent and not independent. So now we need some notation. Let's do some notation right here. Notation. So we have here observed values. These will be noted as O, and so let's just put that right there. So these will be the actual amounts people report. We have here expected, which is E. No, don't do that. The expected value for people to report. We have here, let's see, observed minus expected squared over expected. We have here the chi-squared test statistic. This is going to be a fun test. And let's insert into here. We need an insert symbol, chi-squared. So let's go to equation. Do we see a chi? I might draw the chi. So chi is our little x. Where's it at? I'm totally missing it, and it probably is right in front of me. Oh no, we might have to draw it. Let's draw it out. So chi-squared is going to be our test statistic. How does the chi-squared look? A lot of people say chi-squared, but it's actually chi. So we're going to draw it right here. And so let's write it first. It's spelled C-H-I, but remember it's not chi, it's chi-square. So chi-square test statistic. And we'll put a little parentheses right here, and I'll draw it. So it's like an X with a little tail at the end of it, and it's got the square on it. So I'll draw it really big so everyone can see it's like this, and then you little tail on it, and you do that right there. That's a chi-square. That is the chi-squared test statistic. So you can see what's going on right there. A little hard to draw in the littler box, but let's get one more shot here. Let's do a little tail thing on it, and then do that, and do that right there. Ah, it's a great looking chi-square right there. So that is the chi-squared test statistic, and what that is right there will be, basically, let's try to make sense of it as we talk about it. It's basically our t or z now. So this will be our t or our z that we're basically using, and it's going to give us the standardized difference between the two. So basically, I don't want to basically, the standardized difference between observed and expected, sure, we're going to square it, we'll look at that in a second, used to find p-value like the t and the z. So it's very similar mechanically what we're going to do with it, and luckily for us, the test only goes one way. So it only goes to the right. There's going to be a lot of calculations here in a second. Let's write an example problem. So we have here that we will need to, and let me write a few more things. I can't write more things. We'll watch it as we do it. So we need to write an example question. Let's write here, example problem. And what do we have? We have UT wants to see if there is UT and Florida students report if they think we will go to a bowl game. Let's say 70 UT students think we will go to a bowl game, and 30 say we won't. Why did they say that? 50 Florida students, let's do a meanwhile. Meanwhile, we'll do proper grammar. Meanwhile, 50 Florida students say we'll go. At UT, 70 students think we'll go to a bowl game. Meanwhile, 50 Florida students believe they will go to a bowl game, and 50 believe they won't. Okay, we'll go to a bowl game. There we go. And let's see right here. These students were taking randomly. So I want you to look at this question right here. This is the big part of it. When you go up to someone, you'd have to ask them, are you a UT student? Are you a Florida student? And I hope, I'm gonna see if the audio is still going. I should have been watching that all the time. That'd be so sad if we haven't had audio for this. Yes, we got audio. Whew, I'm gonna watch the audio because we have had the audio go out. And since we only have very few people watching, I'd hate for our audio to go out suddenly. That would be hilarious. But with this right here, these students were, there is audio. It's so good to hear that. I'd feel so bad if I'd been doing this for like the last hour and it was all muted. That'd be so horrible. And good to see you here, Bethlehem. Good to see you in the chat. So these students were selected randomly. We are good to go on this. Guess what? Now we're going to go up there and we're going to take our 4 steps to doing this. Well, we could say, let's write this right here. Yes. Is there, are these 2 variables independent? 2 variables, let's say, is the school, oh, it's doing lag? Someone attends independent, how do I not know how to spell when I slow down? Independent of them thinking they will go, their team will go to a bowl game. Okay, so that's kind of the clue right there. Is the school someone attending? Is the school someone attends? Does the school someone attends? Is the school someone attends independent of them thinking they'll go to a bowl game? Let's go with that. Grammar, we're not here for that. Let's go grab our 3 tests. Here's our 3 tests. We got, or not our 3 tests, our 4 steps. Our 4 steps will be used once again. So let's do it. We're going to go down to a new page, or we're going to go back to the problem, and then we're going to go to a new page on the problem for our 4 tests. Okay, we need to write out the null and the alternative. Guess what? When you do these nulls and alternatives, you will not use statistical notation. For once, I hear people cheering already. You will not use statistical notation. You will simply write, well, don't just write this. You'll hear more in a second. You'll write x is independent of y. And you will write, for the alternative, x is not independent of y. Now don't just write this right here because you have to tell me what x is. School is independent of bowl game prediction. And then we could just take this and we would write school is not independent of bowl game prediction. So school is not, we'll fix this here, independent of bowl game prediction. So that is our null and that is our alternative right here. School is independent of bowl game prediction, and please note that what we have going on right here is we're going to make sure you guys know that this is the x variable right here. School is your x, and bowl game prediction is your y. So you just say x is independent of y, someone's school is independent of what they think about bowl games, their bowl game prediction, and then the alternative would be school is not independent. Very easy one to write out. Two categorical variables. The school someone goes to is categorical, and the bowl game prediction they have is also categorical. Do you think we will go to a bowl game? We will have degrees of freedom in this once again, so sorry I missed a little bit on the notation. We've gotten most of the notation, but let's continue on here. Those are calculation things. Degrees of freedom stands for DF, for degrees of freedom. So let's perform the T, Z, or chi-squared. This one's complicated. So what do we need for this? Whew, it's gonna be a lot of fun. We need to draw this out. Okay. What we would get on the test is something similar to this. We would have UT, and we'd have Florida. We would have yes, and we would have no. And I think I said 70. How many UT students did I say said we'd go to a bowl game? 70 and 30. Cool. So we have 70, 30. Then we have 50, and we have 50. This one is more complicated. It's going to be a lot of fun. There's the 100 UT students, 100. Here's the 200 total. Here's 80, and here is 120. So there are all the numbers we get on the test usually, and if you notice, you might be, sometimes we leave out one of these. Here is a count missing. These are the observed counts. They can be called observed. If we left that out on the test, then you would just say, okay, wait a minute. The total for UT students is 100, so then if we left out that value, this has to be 30, just kind of showing what some test questions could look like. We can sometimes leave out values. These are all the observed values. And now we need to find all of the expected values. And I'm going to show you a trick. The formula for the expected values, which is what I talked about earlier, every expected is equal to, so all the expected values equals row total, that's row total, times column total over grand total. Just to be clear, what are row totals? These are row totals. What are column totals? These are column totals. What is the grand total? That is the grand total. So that is the grand total. The row totals are right here. Those are the row totals. And this is the column totals. Those are the column totals. Now we're not going to do them all at one time. You'll see how it's done. Whenever you're finding out an expected value, I want you to do this. This is my favorite way to solve it on the test. Take your pen and be like, okay, they want me to solve for the expected one right here. If we're solving for Florida, yes, you would take the row total times the column total over the grand total. And do you know what you just did? You wrote the equation. Row total times column total over grand total will give us the expected value for that cell. So in that cell, which I'll draw here in a moment, is going to be 100 times 120 over 200. That will be the expected value for that cell. So let's reverse time here and do that. And I'll probably write a few of these out as we do this. Let's erase all this and let's put an expected matrix over here. So we're going to draw an expected matrix. Sure, now let's make it a little smaller. Perfect, that's what we want. And now we need to do this all right here. We have UT, we have Florida. And we have yes, and we have no. These are all expected values. These are all the expected values. We're going to compute them all. So we're going to compute that bottom left one right away. The bottom left one can be done by 120 over 100, 120 times 100 over 200. That is row total times column total over grand total. So let's solve it, and then I'll show you a trick. 120 times 100 over 200. Row total times column total over grand total, it is 60. So the answer to that equation that I just wrote out right there is 60. So let's put 60 in the cell right here. That is how many Florida students we would expect to say yes. But do you know what's interesting? I can tell you that Florida no is going to be 40. It should be. Hopefully it is, or else I've done something incorrect. Let's check. You should be saying to me, Brian, the formula for that one is going to be, I'm trying to erase that little red dot I got right there. Oh no, we don't want to erase that. 2 seconds, give me a shot. That red dot's here to stay. Let's go here, row total, doesn't matter which order we do it in, times column total over grand total. If you notice, there's the equation, 80 times 100. That points to the cell. Look at the way it points. It points right there to that cell. That is the cell I am solving, and that equation should equal that. We're going to double check the mathematics just in case I maybe made an error. Hopefully I didn't. But let's see. 80 times 100 over 240. How did I know that? Well, think about this. What do these numbers have to equal up to? 60 and 40 have to equal 100. So since I knew 60 and 40 or 50 and 50 equal 100, I know 60 and 40 have to equal 100. Now you can solve out the remainder of these if you want by doing them all by hand, such as 120 times 100, because you can do it either way, over 200. If you notice, that's actually the same value. We're actually going to get the same value as we did previously, and we'd get 60. And then the same thing would occur there, and we'd get 40. If you notice, these add up to 120, and these add up to 80, which are the respective values for the totals below. So your expecteds have to equal up to the row totals and column totals that they were taken from. And of course, the grand total has to be found in what you have too. We're almost done. Ooh, the math for this one is quite fun. But now we need to find the chi-squared test statistic. So let's go down here and find the chi-squared test statistic. Those are the expecteds. So with our expecteds found, we have to do one last formula here, and this is what we'll be covering next class. We need to do the formula, which is observed minus expected squared, quantity squared, over expected. This equals to a cell chi-squared. This is equal to a cell chi-squared. Observed minus expected squared over expected is equal to a cell chi-squared, which means, yay me, and we don't write test questions this long usually, I have to solve out all of these. So I'm going to write out this for you to see right here. We're just going to do a little practice of it. In this cell right here, I need to make my chi-squareds. So if we go here and we write a chi-squared right here, these are the cell chi-squareds. So these are all my cell chi-squareds. I want you to look at the observed for this cell and the expected. Remember, the formula is observed minus expected squared over expected. And I did put the expected there. Hopefully I don't make any math errors. But this is observed minus expected squared over expected. Luckily, since we're squaring it, it doesn't matter which way we subtract it. But in that cell, let's erase all the mathematics we drew out. What are we going to get for the first cell chi-squared? If you notice, it's 70 minus 60. We're going to square that, so we get 100. And then we're going to divide that by 60. And the first cell chi-squared is 16.666. Did I do that right? No, I think I made an error. I typed 6. Because I was thinking that's not what it should be. There you go. So I forgot a 0 on the 6, and that's how errors can happen. Hopefully we haven't made any today. So the cell chi-squared here is 1.6, repeating. And then the next one, we're going to do observed minus, so we have observed of 50. I'm doing the bottom left one now, Florida yes. Minus this, we're going to square that, that's 100. And then we're going to divide that by the expected. Do not divide by the observed. And once again, we get 1.666 right here. And now we have to do 40 minus 30. This will give us a little bit of a different number. But, excuse me, 30 minus 40 to be technical. 30 minus 40. and that gives us 100 again when we square it, and then we divide that by 40. You might say, why are you dividing it by 40? Well, it's because, and let me explain why with the next one, we are doing observed minus expected, so it's 30 minus 40 squared, which gives us 100, over the expected. The expected is the equation, observed minus expected over expected. That's what we're solving out right there, observed minus expected over expected. So just notice how I have my observed matrix, my expected matrix, and now I'm getting my cell chi-squared matrix. And the last one right here, the final cell chi-squared will also be 2.5. So that's what we got going on. We're almost done. We're on the downhill on this one. Woo, we got it. If I am correct, I believe the test chi-squared is going to be 8.33. All we do to get the test chi-squared is we add up all the cell chi-squareds. By adding up all the cell chi-squareds, we should get, I believe, 8.333, and we do. All you're doing to get your test chi-squared is, so let's write chi-squared equals sum of cell chi-squareds. So all I did was add up all those values to get the test chi-squared. One more step and we're done. To find the p-value, we have to plot this. The degrees of freedom for this are simply, and it's such a fun thing to do, the degrees of freedom for this one are n minus 1, so let's write here df, and that's not OF, that's df, equals rows minus 1 times columns minus 1. So let's write it so you can see what it's not that hard to write out cols and rows. So rows minus 1 times columns minus 1. That's columns minus 1. What are you doing? All you're doing is taking and deleting one row and one column. How many degrees of freedom does that make when you do 2 times 2, you subtract from that and do 1 times 1? There is 1 degree of freedom for this. So the degrees of freedom for this test are 1, and here's how I ask my students to remember it. When you think about this test right here, if it's a 2 by 2 matrix, hold up your hand with 2 by 2, and then 2 times 2, drop it to 1 times 1. What if you had a 2 by 4 matrix? There's different ones we can do. If it's a 2 by 4 matrix, drop it down to 3 times 1. A 2 by 4 matrix would have 3 degrees of freedom. And you can double check this out right here. You can make sure by drawing a 2 by 4, 2 rows, 4 columns, and you go 1, 2, 3 right there. And then what do you get? If you delete off 1 row and you delete off 1 column, lo and behold, there are 3 degrees of freedom. So that's a 2 by 4 showing that it has 3 degrees of freedom. Just kind of drawing that L, delete 1 row, delete 1 column. Do not think this is a 3 by 3. There are UT students, there are Florida students. There's yes, there's no. It's two two-level categorical variables, and that's what we have going on right here. So we now have our test chi-squared, which was equal to the test chi-squared. So that is the test chi-squared is 8.333, repeating, and the degrees of freedom are equal to 1, and we're almost done. We have now the chi-squared test statistic. Find that p-value. Woo, on the downhill. So now we need to go back to our site. Back. And here we are. Let's put in the degrees of freedom is 1, and let's do it. The chi-squared is a bit of an interesting distribution. It's a right-skewed distribution that actually becomes more normal as the degrees of freedom get higher, but we notice here that ours is very right-skewed due to low degrees of freedom. And look at that p-value. We got basically no area under the curve telling us our results or results more extreme were unlikely due to random chance. You know what we're going to do. We're going to reject that null. So the p-value here is 0.004. It is harder to draw out the chi-squared. I will say this, this question is one of them. If you've done enough chi-squareds, you know a chi-squared of 1 is this heavily skewed distribution. Chi-squared of 1 is extremely right skew. It looks like that, and usually about after 3 you've got a decent hump. That's like a chi-squared of 3, and then after you get to maybe around 30 degrees of freedom, it starts to look pretty normal with the center being the degrees of freedom. So you can see right here with 3, you start to see the bump right there, and then if you get to 30, it starts to look somewhat normal, and then if you get to a high enough, which that is not calculating properly, because the degrees of freedom should be the center of the curve. These are things you don't need to know right now, but you should just know to go to the applet and put in your degrees of freedom. This will draw the curve out for you. We're then going to plot our chi-squared right here, and we're going to find our p-value. And since the p-value is low, what are we going to do? P-value is low, reject that null. You know what's happening. Let's take a look back here. So the truth is we do have this curve right here. We landed all the way here at 8.333. This is a very small p-value. Was it 0.004? I think it was. We're going to double check that p-value. 0.004, if you can't see, there's the p-value right there. My drawing on this one is not as pretty as the other ones. So the p-value right here, that is the p-value right there. When the p-value is low, we reject that null. Good job for UT. We're going to end on a high note for Rocky Top today because we're going to say we reject the null hypothesis that school is independent of views on bowl game. We have evidence to suggest, thank you, to suggest that someone's view on a bowl game is not independent of the school they go to. Sometimes on follow-up test questions, we've asked you to maybe tell us what direction does it go. And you know what? We're going to end, because I really want to see how right we were. We're going to throw this into jump real quick right here and make sure we did it correctly, and we're actually going to view the visualization of it. So let's hop in here to jump, open up a new data sheet, and do it. So we need right here is school. And we need right here is bowl game. And this will be help for the homework assignment if you're doing those. You can enter this into jump. So this is a little homework help. And you need here frequency. It can be called whatever, but nicer to call nicer things. We have school UT, Florida, Florida. Then we have bowl game, yes, bowl game, no, bowl game, yes, bowl game, no. And I think I said 70 UT students and 50-50 for Florida. So as long as I put in the right numbers right here, and then 50-50, and what do we notice? Let's do the fit y by x. This is recorded, so you can slow it down later if you like. Let's put this into the frequency. That's just the count. We want to see if somebody's school, remember when we said school is the x, explains the bowl game, and let's go here to calculate. And what do we see? Pearson. Pearson's where your p-value is at. Remember that p-value of 0.004? We did that work by hand, and we got that Pearson chi-squared of 8.333. So we did it. There's other tests like Fisher, good old Ronald Fisher.